This is Lecture 7, Difference of Means Test. By the end of this lecture, you should be able to write null and alternative hypotheses, construct a mean comparison table, interpret a mean comparison table, conduct a difference of means test, interpret a difference of means test, and know when to use a mean comparison table and difference of means test to assess the relationship between two variables. A mean comparison table allows you to use simple tables to analyze the statistical relationship between two variables. It is most useful when you have a nominal or ordinal level independent variable and an interval or ratio dependent variable. Recall that both nominal and ordinal level variables separate observations in your dataset into different categories, while interval and ratio level variables are continuous. To demonstrate how to create a mean comparison table, I will start by using the following hypothesis. Dictatorships spend more on defense spending as a proportion of GDP than democracies do. Note that the independent variable institutions is a nominal level variable, dictatorship/democracy, while the dependent variable defense spending is a ratio level variable as it is ordered and continuous and has a true zero. Now let's say I wanted to determine if there really was a real-world relationship between institutions and defense spending. I could collect data on types of institutions in a country and how much that country spent on defense as a percentage of GDP. Here is what a hypothetical data set of that type would look like. To set up the mean comparison table, you put the independent variable name in the first column heading. Then you put the independent variable category names in the rows underneath. Then you add a total row at the bottom. Then you write the dependent variable name and the term mean score in the subsequent column heading. So in our example, since institutions was the independent variable, I put the term institutions in the first column heading. Then I wrote democracy and dictatorships in the next two rows underneath, as they are the categories of the independent variable. Then I made a total row at the bottom. Last, I placed the term defense spending mean score in the subsequent column heading. Next, you calculate the average of the dependent variable for each category of the independent variable. The average is the sum of all the cases for the dependent variable in one category of the independent variable divided by the total number of observations in that category. So for the democracy category, the calculation will be 0.05 plus 0.03 plus 0.02, and that value divided by 3 because you have 3 observations. 1, 2, 3. Hence, the average defense spending as a proportion of GDP for democracies is 0.03. For the dictatorship category, the calculation will be 0.15 plus 0.08 plus 0.10, and that value divided by 3 because you have 3 observations, 1, 2, 3. Hence, the average defense spending as a proportion of GDP for dictatorships is 0.11. In the total row, you will find the overall average of the dependent variable for all observations. The calculation is 0.05 plus 0.03 plus 0.02 plus 0.15 plus 0.08 plus 0.10, and that value divided by 6 because you have 6 observations. 1, 2, 3, 4, 5, 6. The average for all observations was 0.07. Next, you count the number of observations that each category of the independent variable had and write that number under the mean score for the category in parentheses. So the democracy category had 3 observations. So we write a 3 in parentheses under the mean score for democracy. The dictatorship category had 3 observations. So we write the number 3 in parentheses under the mean score for dictatorship. And there were 6 observations total, 3 plus 3. So we write a number 6 in the parentheses under the mean score for all observations. One way to interpret the mean comparison table is to compare the mean values of the dependent variable between the categories of the independent variable. So in this case, the mean defense spending as a proportion of GDP for democracies was 0.03, while the mean defense spending for dictatorships was 0.11. So it does seem like dictatorships spend more in defense than democracies do. You can also compare the mean values of the dependent variable for each category of the independent variable to the overall mean of the data. The mean defense spending for democracies was 0.03, which is less than the overall mean of 0.07, and the mean of dictatorship was 0.11, which is greater than the overall mean of 0.07. Based on all of this information, we can conclude that dictatorships spend more resources on defense spending on average than democracies do. In this part of the lecture, I will review what a mean comparison table is and then discuss how to conduct a difference of means test. Imagine you wanted to conduct a study that analyzed factors that influence ideology in the US. In this study, ideology is your dependent variable. To measure ideology, you collect data from the Comparative Manifesto Project, which measures each party's ideology using information from their party platforms. Negative values indicate a party is more liberal, and positive values indicate a party is more conservative. Note that this is an interval level variable because it is ordered and continuous but has no true zero. Imagine you believe that party identification influences ideology. Party would be your independent variable. Note that it is a nominal level variable because it separates observations into categories, Democrat, Republican, and the categories have no inherent order. Republicans are not greater than Democrats, Democrats are not greater than Republicans. You believe that Republicans are more conservative than Democrats are. Party, Republican versus Democrat, influences ideology. Because you have an interval level dependent variable and a nominal level independent variable, you can use a mean comparison table to determine if the mean ideology for Republicans is greater than the mean for Democrats. You place the party categories, the independent variable, in the rows. So Democrat, Republican. And then in the next column, you place the mean of the ideology score for each category of the independent variable. So Democrats had a mean ideological score of negative 9.75, and there were 23 observations for Democrats. And Republicans had a mean ideological score of 12.06, and there were 23 observations for Republicans. The overall mean for all observations for Democrats and Republicans was 1.16, and there were 46 observations overall. In order to assess whether the independent variable had an effect on the dependent variable, you compared the means of the dependent variable across the categories of the independent variable. You can also compare the mean of the dependent variable for each category to the overall mean in the total row. So applying this to our example, the mean of Republicans was 12.06, which is much greater than the mean of Democrats, negative 9.75. You can also say that the mean of Republicans was 12.06, which was much greater than the overall mean of 1.16, and the mean of Democrats was negative 9.75, which is much less than the overall mean of 1.16. Based on this information, it does appear that Democrats adopt more liberal platforms than Republicans do. Even though the mean comparison table indicates that there is a difference in the means of the ideological positions of Democrats and Republicans, is the difference in the mean of the dependent variable for each category of the independent variable large enough to indicate that the independent variable really does have an impact on the dependent variable? We will likely always see minor differences in the mean of the dependent variable between categories of the independent variable, even if there's no real causal relationship. We need to determine if the differences we observe in the means are large and consistent enough to confidently conclude that the independent variable really does have an impact on the dependent variable. To do this, we can use a difference of means test. A difference of means test helps us determine if the difference in means of the dependent variable between the categories of the independent variable are positive, negative, or indistinguishable from zero. This allows us to confidently conclude that the effect of the independent variable on the dependent variable is large and consistent enough to conclude that the independent variable actually does have a statistical impact on the dependent variable. Note that this test is useful when we have a nominal or ordinal level independent variable with only two categories and an interval or ratio level dependent variable. In the next part of the lecture, I will take you through the steps of conducting a difference of means test. Imagine you wanted to conduct a study on variations in ideology. In this study, ideology will be your dependent variable. Imagine you believe that party identification influences ideology. Party would be your independent variable. You believe Republicans are more conservative than Democrats are. Party, Republican versus Democrat, influences ideology. Another way to state this hypothesis is that there is a difference in the mean ideological positions of Republicans and Democrats. To analyze the relationship between party and ideology, you collect data on each party's ideology using information from their party platforms, which indicates their positions on different issues. Negative values indicate a party is more liberal, and positive values indicate a party is more conservative. You could use a difference of means test to determine whether Republicans and Democrats have different ideological scores based on this data. Whenever we want to determine whether there is a difference in the mean of the dependent variable for two different categories of the independent variable, we begin by writing two hypotheses, a null hypothesis and an alternative hypothesis. The null hypothesis always states that there is no difference between the means of the two samples. Samples in this context is just another way to say two different categories of the independent variable. The formal way to write a null hypothesis is to write h subscript 0 colon x subscript 1 bar is equal to x subscript 2 bar, or the mean of sample 1 is equal to the mean of sample 2. Next, you have to write an alternative hypothesis. Your alternative hypothesis should always have a direction. So either it should state the mean of sample 1 is greater than the mean of sample 2, or it should state the mean of sample 1 is less than the mean of sample 2. The formal way to write the alternative hypothesis is to write h subscript 1 colon x subscript 1 bar is greater than or less than x subscript 2 bar. Going back to the original argument from the beginning of the lecture, let's assume that conservative positions are greater than 0 and liberal positions are less than 0. Applying this to our example, our null hypothesis should be the mean ideological value of Republicans is the same as the mean ideological value of Democrats. Our alternative hypothesis should be the mean ideological value of Republicans is greater than the mean ideological position of Democrats, since conservative positions, which we expect Republicans to take, are greater than liberal positions, which Democrats are supposed to take on this scale. The next step is formulating a decision rule. You will choose one of the following statements. Note, as you can see below, that throughout the difference of means test, you are going to be using two t-values. One you actually calculate, and one from the t-table that you will see in this lecture. So, choose one of the following statements based on the direction of your alternative hypothesis. If the t I calculate is greater than the t value from table 6.4 in this lecture, The difference is greater than 0. There is a positive difference in means. Otherwise, I do not know if there's a difference in the means of the samples. This template here is for when you expect there to be a positive difference in means. Next, the other template you could use is, if the t I calculate is less than a negative t-value from table 6.4 in this lecture, the difference is less than 0. There's a negative difference in means. Otherwise, I do not know if there's a difference in the means of the samples. You will use this statement if you think there should be a negative difference in means. An easy way to tell whether you should choose the first or second statement is by looking at your alternative hypothesis. If it has a greater than sign, the difference in means should be positive because when you subtract a smaller number from a larger number, you get a positive number. In this case, you should pick the first statement as you expect the t you calculated to be greater than the positive t-value. If the alternative hypothesis has a less than sign, the difference in means should be negative because when you subtract a larger number from a smaller number, you get a negative number. In this case, you should pick the second statement as you expect the t you calculate to be less than the negative t-value. Before we move forward, I want to explain to you why we are creating these decision rules. The decision rule you create will help you know at the end of the process whether there is a difference in the means of the samples. So for example, if you think there's a positive difference in means and the t-value from table 6.4 that you used in your decision rule was 1.684, if the t that you calculate is greater than 1.684, then you can say there's a positive difference in means. If the t is less than 1.684, then you would say that you don't know if there's a difference in the means. Alternatively, if you think there's a negative difference in means and the t-value from table 6.4 that you use in your decision rule was negative 1.684, if the t you calculate is less than negative 1.684, then you could say there's a negative difference in means. If the t you calculate is greater than negative 1.684, then you say that you don't know if there's a difference in means. Going back to our example, our alternative hypothesis suggested that Republican platforms should be greater than Democratic platforms. Since this is a greater than sign, we expect a positive difference in means and should choose the first statement. If the t I calculate is greater than the positive t-value from table 6.4, the difference is greater than 0. There's a positive difference in the mean platform positions of Republicans and Democrats. Otherwise, I do not know if there's a difference in the means of the samples. Next, we have to find out what t-value from table 6.4 that we need. Note that you should only be using table 6.4 in this lecture for this step. Recall that the row you use in table 6.4 is based on your degrees of freedom, which is the number of observations minus 1. In a difference of means test, the number of observations equals both the number of observations from sample 1 plus the number of observations from sample 2. If you cannot find a degrees of freedom row for your degrees of freedom, use the closest lowest value. In addition, to find the t-value from this table, you should always use the 0.05 column for a difference of means test in this course. So applying this to our example, we had 46 observations, 23 for Democrats and 23 for Republicans. So 46 minus 1 is 45. So our degrees of freedom row is 45, but there is no 45 row. The next closest lowest one is 40. Next, use the 0.05 column. The t-value from table 6.4 in this lecture that is associated with the 40 row and the 0.05 column is 1.684. So we insert this t-value into our statement. If the t I calculate is greater than positive 1.684, the difference is greater than 0. There's a positive difference in the mean platform positions of Republicans and Democrats. Otherwise, I do not know if there's a difference in the means of the samples. Please note, if we were using the less than template, you should insert the t-value with a negative sign. It would have said, if the t I calculated is less than negative 1.684. Now that we have our decision rule, we can calculate our t-statistic. T equals the mean of sample 1 minus the mean of sample 2, and that value divided by the standard error of the difference. The t-test here takes into account how much the means of the two samples differ. It also takes into account the standard deviations of those two samples. The means of the two samples have to be far enough away from each other to be considered statistically different. In addition, observations cannot vary too far away from the mean of each sample. If the means of the two samples are different, but observations from each sample vary too much, this leads observations from both samples to overlap, meaning the sample means would not be different from each other. The first step in calculating the t-statistic is finding the means of both samples. The mean for Republicans was 12.06, and the mean for Democrats was negative 9.75. Next, we calculate the numerator. The numerator is the mean of sample 1 minus the mean of sample 2. Remember to subtract the samples in the correct order based on your alternative hypothesis. Sample 1 was for Republicans. Sample 2 is for Democrats. So the Republican platform mean was 12.06 minus the Democratic platform mean negative 9.75, which is equal to 21.81. So 21.81 is the value of our numerator. Next, we calculate the denominator. Recall that the denominator was the standard error of the difference. The standard error of the difference of the two sample means is calculated as follows. The square root of the sum of the squared standard errors of each sample. The standard error for a sample is just the standard deviation divided by the square root of the number of observations. So, applying this equation to our example, the standard error of sample 1 was 2.2. The standard error of sample 2 was 1.68. So the first thing you should do is square each standard error. 2.2 squared is 4.84. 1.68 squared is 2.82. Then you add 4.84 and 2.82 together, which is 7.66. Then you take the square root of 7.66, which is 2.76. 2.76 is your denominator. Now you divide. 21.81 divided by 2.76 is 7.9. 7.9 is the t-statistic you calculated. Now you go back to the decision rule and compare the t-value from the decision rule and the one you calculated. We stated that if the t I calculate is greater than positive 1.684, the difference is greater than 0. There's a positive difference in the mean platform positions of Republicans and Democrats. Otherwise, I do not know if there's a difference in the means of the samples. The t-value we calculated was 7.9, which is greater than 1.684. Therefore, there's a positive difference in the means of the platforms of Republicans and Democrats. After you have analyzed your results, if you found that there was a difference in the means of the samples, you could add additional analysis to your conclusions. So first, you could add, the null hypothesis stated that there was no difference in means. I reject the null hypothesis. As the alternative hypothesis predicted, there is a positive or negative difference in means, and the difference is significant. Then you would add the discussion of the specific effect of the independent variable and the dependent variable. Applying this to our example, we can conclude, I can reject the null hypothesis. As the alternative hypothesis predicted, there is a positive difference in the means, and the difference is significant. And then you add the discussion such as Republicans are more conservative than Democrats are. Now imagine that the t you calculated was 1.15, which is not greater than 1.684. Then you could not conclude that there was a difference in the means of the samples. If the difference between the means was not different than 0, meaning that there was no difference in means, you would add, I failed to reject the null hypothesis. I cannot conclude whether there's a difference in the means of the samples. There is no evidence that the independent variable influences the dependent variable. You simply do not know, and you do not add any more discussion. I am going to discuss one more example of the difference of means test just to make sure that you have multiple examples of how they work. Imagine we had voter turnout as our dependent variable and gender as our independent variable. Our null hypothesis would be the mean voter turnout of men and women are equal. Our alternative hypothesis could be the mean voter turnout of men is higher than the mean voter turnout of women. Imagine our decision rule was if the TI calculate is greater than positive 1.646, the difference is greater than 0. There's a positive difference in the mean turnouts of men and women. Otherwise, I do not know if there is a difference in the means of the samples. And the t we calculated was 1.10. 1.10 is not greater than 1.646. Therefore, I can conclude I fail to reject the null hypothesis. I cannot conclude whether there's a difference in the means of the samples. There is no evidence that the independent variable influences the dependent variable.